hello to all my friends. Okay. Oh. All right. Well, I hope that everybody listens to all the previous talks before they listen to this one. And I learned a lot from the earlier talks. I learned that that a good talk is supposed to have a joke and a theorem, and well, this one won't have either of those. No. I mean, a joke has to be something funny. It's not necessarily something that people laugh at. I have a lot of friends that laugh anyway. My daughter says, that just because people laugh, you shouldn't think you're funny. So, all right, let's see. You're supposed to, kill your darlings? Is that what you said?
That's what I heard,
Yeah, so I killed all my darlings. Okay, all right. Then there was a question about kosher words, unkosher words. And, but here you discover that the question of what's kosher and unkosher is sometimes subjective. So what I'm going to do is I'm going to, we had all this beautiful language about testability and non-standard analysis, and I'm going to treat that as, it's really beautiful in its own right, but, I'm going to just put it into a different language, a more geometric language. Okay, so let me give you a new principle, which is that no day deserves more than 2 good talks. Okay, and you would be really spoiled to get 3. So I don't think so.
You won't be spoiled.
I don't plan to spoil you. No, it's very kind of the previous 2 speakers to give the introduction to this talk. So let me get to what I want to do is I want to explain why for lots of gammas there are almost homomorphisms to almost homomorphisms, I'll tell you, to, say, the orthogonal group with the operator norm, or the unitary group. You'll see it's a little bit easier to work with the unitary group than the orthogonal group, but it doesn't make a difference for the shape that I want to explain, that are not almost homomorphisms. That's the, okay, good. Okay, so because I remember when Ulam published the translation of the Scottish book, because I didn't read it in the original Scottish, in the original Polish, he explained that there's a general way of getting problems, which is that for any notion of x, you could ask if things that are almost x are almost x's. Okay, and I think that that's what we call testability, and that's what we were doing here with these almost homomorphisms. The question is, are not almost, so you want to say are not nearly. And that captures the difference. And I find that it's easier for me, in spoken English to just say that these almost homomorphisms are not almost homomorphisms. Okay, but when you write it down, right, that pause is very easy to do verbally, but it's hard when you write papers. And it was actually not hard when you write papers, it's hard to get past referees.
There are 2 papers in the literature. The title of one of them is the following: Every nearly commuting matrices.
Oh, you see, instead of almost commuting.
Near commuting matrices.
Uh-huh.
And there is another paper. The title says, not every nearly commuting matrices are near commuting matrices.
Uh-huh. And it has to do with the norms.
Both papers are correct. There is no fundamental mistake in mathematics.
Yeah.
This Ulam is
the Scottish book? So the Scottish book was the Scottish Cafe. Yeah, it was, and it was a cafe, and people would come and discuss mathematics at the cafe, and I think it was more like a bar than a cafe, actually. And then you would ask the barkeep when you finally had a good question or comment, then you'd ask for the book and then you would write it down.
It wasn't in Scotland.
No, it was a Scottish cafe in Warsaw. No? Lvov? Okay, by the way, nothing here is going to be quite true. Things are going to be almost true. So if I say Warsaw and it's Lvov, that's, right. Okay, so this is what I want to do. I just want to explain this fact, and also, and why it's interesting, or maybe better would be useful. Where did these come up from? These came up from somewhere, and in the previous talk, the focus was that you really wanted this to be true, that you want the almost homomorphisms to be almost homomorphisms, and then you use them to say, get a failure of approximation or something like that. So here, these objects came up extremely naturally, and the ideas that I want to explain are due to Gromov and Lawson. And then re-explicated in a paper of Kahn, Gromov, and Moscovich, a contra-undo note. And then Alex and I had some conversations because of the budget at the Stable Care meeting. We had to share a dorm room. So, I'm not going to publicly say that sometimes math is improved by having a little bit of a worse budget. But, yeah. Okay. Okay, so the title was, I forget, almost flat bundles. Okay, so let me start off with bundles. Okay, right. So I don't know if this is a kosher word or an unkosher word. Okay, it's more it's very much a part of continuous mathematics. Okay. Yeah. So here. Okay, so here's a space. Oh, okay. All right, here's a space. Okay. Okay. So you have E. So this is a situation. You have E to B, and it has some fiber. This is the picture. Okay, I'm hoping that that this is maybe a reminder. Okay, and we're going to be interested in vector bundles. Okay, so the situation is this. So B is called the base. Okay, in all of the examples, examples I'm planning to discuss, the base is going to be, either a manifold or a moral manifold, like a building modulo a discrete group. Okay, so it's not really a manifold at all, but it's certainly a decent space. Okay, then E is the total space. It doesn't, it just lives there as a bookkeeping device. It's part of the mathematics, but okay, there's this projection map. The key point is that pi inverse of any point little b is supposed to be isomorphic to a vector space. Okay, that's sort of the basic situation. Okay, and really you don't want this to be entirely random, that at each point it's a different vector space with nothing at all linking them together, right? So really you assume that for all b there exists a little neighborhood O sub b containing b, such that pi inverse of O sub b is isomorphic to v cross O sub b in such a way that projection down to O sub b such that, in these coordinates, projection is obvious. Okay? And then I also want there to be, part of the data is that the fibers, right? So these individual inverse images are called fibers. Okay? I want the fibers, the vector space structure is part of the data. Okay, I mean, I don't want to be explicit about that, but it's actually very important, and it's important even in the even in the examples. Okay, so this is okay. So this is what a vector bundle is. So what I want, concretely, right? I mean, so these things are. Okay, so let's think about the case where the base is a circle. Okay, so what's going on? All right, so we could think very concretely about what's going on, right? So we're going to have this bunch of open sets, and then the circle is compact. So there aren't finally many of them. Okay, so so over this interval, it looks like this across the vector space V. Okay, and now over here, of course, it's supposed to be this cross V prime. All right, but you know what's going on the overlap. So on the overlap, you have an isomorphism between V and V prime, and you don't run into any trouble at all. Therefore, making this, just getting a trivialization over the larger interval. Okay, so what goes on? The only place where things get exciting is when you finally finish, the last circle. I mean, the last point, and it closes up. And then the difficulty is, right? So then when you close up, you get an element of the general linear group of that vector space, right? That describes, right? I mean, having decided, that you're always, how to, if you like, give a basis, right? You just imagine this transporting bases on all of the fibers. So you know how to trivialize all the fibers as you get around. But then finally, when you come back, you can't use it again, right? I mean, this, that last interval has sort of two places of overlap with what happened before. So you could fix one of them, but it's at the cost of now having maybe an incompatibility with the other one. And now here you could imagine that it makes a difference whether you're real or complex. If you're real, right, then the general linear group has two components, right? I mean, right there's the determinant that goes to the non-zero reals, right? There are two components. So you either have positive determinant or negative determinant. So if you have negative determinant, then you really run into an incompatibility. And
is it part of the definition that eventually this monodromy will be linear map? The face of
yeah, no. I mean, right. That was part of what I said, that each of the fibers has a linear structure. Okay, right? So that was why in the end it would be linear. If I would have just said that you had a homeomorphism, then over here I would be stuck using homeo of V. Okay? All right? So, right, so, what this, and then you run into the words of what are the structure groups of the bundles. Okay? What kind of additional structure does there have to be, right? So if you took the most naive definition, at this point you would have homeo of V. Okay, it still is a theorem that homeo of V has two components, but that's a much harder theorem. Okay, that's a theorem of Kirby. Okay, basically, it's the torus trick. The hard fact is to know that if a homeomorphism of Euclidean space is orientation preserving, then it's actually isotopic to the identity. Right, pi 0 of homeo has to do with the isotopy class of homeo. Okay, no, those are unkosher words, and in fact not necessary for the talk. So. Just let me skip them, but, okay, so, right, so in this case, okay, so if the determinant is positive, then there's a family, then I could sort of use that family, right, that family of matrices, of non-singular matrices, to change the basis, to make the basis that I have at the beginning of the interval compatible with the basis that I have at the other end of the interval. Okay, right, so I'm just exactly interested in components of this, okay? But if I were in the complex case, then this wouldn't work, right? The general linear group of the complex is the determinant, so to speak, right? I mean, we go to C minus the origin, right? I mean, there's only one component of that, and in fact, there's only one component to GLNC. Okay, so I wouldn't get non-trivial bundles over the circle, right? They're non-trivial, right? There are non-trivial real bundles, there aren't non-trivial complex bundles. Okay? Okay. same reasoning, tells you something about vector bundles over the n-sphere. Okay, that the vector bundles over the n-sphere, they turn out to be exactly, now this is going to be non-kosher, pi n minus 1 of GLV. Okay, so let me just interpret, the symbols. Okay, I won't have to prove anything because, this is just some background. Okay, so V is the vector space, that's the fiber. This is the general linear group. Okay, pi n minus 1 means maps from the n minus 1 sphere into the general linear group. Okay, and so what does that correspond to? So here, okay, I can, right? Da Vinci said that if you could draw a circle, you're an artist, or you could draw anything. I don't know what Da Vinci said, come on. I know he was in Italy somewhere, Rome, Pisa, I don't know. Okay, love. Yes, there's always an epsilon involved in almost. Okay, so this is the n-sphere. We know it's a union of two n-balls. Okay, I have no trouble knowing that I wanted to have a disk cross V on top and a disk cross V on the bottom. Okay, however, if I have now a family, F sub theta, F of theta, where F is a map from the n minus 1 sphere into the general linear group, right? I could decide, oh, well, here I have the basis for V, okay, and over here I have a different basis for V, and I will identify this basis with that basis using at the point theta, using the transformation F of theta. Okay, right, so for every map from the sphere to the general linear group, you could build a bundle. Okay? And this is exactly the analog of what we did in the circle, okay, except that, okay, there's one comment, which is that I should choose one point where I make where I pick an identification, right? That was, so when we started with the circle, we really, I said we went around. I could have thought of it as being on two different intervals, making it trivial, and then at one side, fixed the identification at one point, and then the rest. Okay, and that's exactly what's going on here. Okay, so this is what bundles look like, and made. Okay, let's see. Almost flat bundles. Okay, and we're still just on the bundles. Okay, then we're going to have to talk about flat, and then we'll talk about almost flat, and then we'll have to talk about almost flat bundles that are not almost flat bundles. Okay, right? I mean, that's where we're going, I hope. Okay? So it turns out that when the dimension of V is bigger than n, then this homotopy group stabilizes. Okay? In other words, if I look at 50-dimensional bundles over something that's two-dimensional, I mean, most of those extra dimensions don't matter. Okay, so, just in fact, the three, once it's more than three-dimensional, you didn't benefit. In fact, every three-dimensional bundle splits as a two-dimensional bundle plus a trivial line bundle. Okay, those are the fancy words. I'll tell you what the answers are. Okay, so for the real case, and there's the complex case, these are both due to Bach. Okay, a really revolutionary result. So in the complex cases, the answers are 0, Z, 0, Z. So this is pi 0, right? That there's only one connected component. Okay. U1, right, is the circle. Pi 1 of the circle is Z. There's a determinant map. Okay, that if you take the general linear group, there's a map to the circle. So that, the determinant gives you a way of seeing that pi 1 of the unitary group is Z. And then he says it's a twofold periodic answer. So it's 0z, 0z, 0z. This is what pi I, of GLC, right? Of the stable answer, right? I mean, so this means GL infinity, but where infinity really means any big finite number. Okay, I don't want to discuss, right? Later on, we'll have to talk about, more subtle things. Okay, so this is what the answer is for the complex case. So what this means is that sort of stably there exist sort of Z's worth of bundles on even dimensional spheres. Okay, so if you have an odd dimensional and nothing on odd dimensional spheres. Okay, so this is called Bach periodicity for obvious reason. The answer is 2 periodic. Okay, and apparently he got to this by calculation that there was an early claimed result that was 0z, 0z, and then at pi 9 there was a z mod 3, and Bach couldn't believe that, and he realized, I believe it's periodic, so then that's a really worthwhile thing to try to prove. Okay, so anyway, there are many, many proofs nowadays. And for the real case, I'll just tell you the answers. And then periodic. Okay, this one is 8-fold periodic. Okay, and a long, beautiful story, not really relevant to the talk. Okay, and there's another beautiful story that's even more irrelevant about what could you put in the middle that would be 4 periodic. Okay, right? I mean, right? There should be something. Okay. Okay. So let me, right, so here's my B, here's an O sub B, here's an O sub B prime, okay? And to be a vector bundle means that really I have these transition maps, O sub B cross V to O sub B cross V prime, right, which are fiber-wise linear, right? That was the structure that we talked about so far. Okay? Okay? There are 2 things I should discuss. So one is that I can put on additional structures. On the fiber, for example, I could put on an inner product structure. Okay? And demand that this is preserved. Okay? I mean, I could do whatever I want. I mean, I started off by saying homeomorphism, right? And then I decided we wanted linear structure. Now you could go ahead and say that you want the structure to preserve distances. Why not, right? So of course, in the real case, I mean usual inner product. Otherwise, I mean Hermitian, right? I mean, you could do these things. And, it's a standard construction. On every vector bundle, you can do this, partitions of unity. Okay, that boils, how would that change all the formal junk I said? So then instead of being the general linear group, what it will have to then be is an orthogonal group, right? It will have to be the group that preserves that structure. But of course, to a topologist, O of V and GL of V, right? Well, this is in fact the maximal compact subgroup of this Lie group, okay? And one knows that that if you take a Lie group and you mod out by its maximal compact, what's left is always homeomorphic or diffeomorphic to Euclidean space. That usually has a non-positively curved structure. See, curvature came in. You see, that was either foreshadowing or foreboding music. Okay, I don't have a soundtrack, but I presume that when they edit this for the YouTube, they'll add a soundtrack. Okay, and you know. What, am I Darth Vader? Is that what you're saying? Not okay. Okay. So in fact, there's no right. So that's where that comes in. That there's no difference in the topological story. But of course, the geometric story becomes enormously different, right? By imposing this kind of structure and on the fibers, then that enables you to begin putting more geometric structures on the bundle and getting more refined structure. Okay? So that's sort of point number one. Point number two is I could be even more violent. I can demand that on the overlap, the function, right? So now I have this thing that goes from OB intersect OB prime cross V to, well, I have a map from this, let me say, to the isomorphisms from V to V prime, right? Right, that was sort of the structure that we have locally. I could ask that this is locally constant. Okay? Okay, right, so what's an example of a locally constant map? I don't know, the identity map, right? Suppose it was the identity. Okay, the constant map was the identity map. Okay, so then I would be getting the trivial bundle. Okay, so what happens with this locally constant? Okay. Okay, so let me just comment, these locally constant bundles, that's exactly the same thing as what people call flat bundles. Okay? It means that you have some way of identifying all the nearby fibers in a completely standard way, sort of locally, right? I mean that, that in these little coordinate patches, there are sort of canonical identifications between what's going in from fiber to fiber, so that therefore when I'm having two overlapping neighborhoods, the nearby ones, what I did at one point determines what's going on. But if I have several components, okay, if I have several components, right, then then I might be, then I might have, then on each one I might be twisting a different way. Okay, so what's the standard example of this? The standard example would be, suppose that I have rho being a map from Z into, say, the general linear group of V. Okay, what I could do is I could take, this is 0, 1 cross V, okay? And then I identify this via row of 1. Right, I use row of 1 in order to glue this to that, okay? And that will be a flat bundle. Right, I mean, when I go ahead and I do this, sort of all the nearby fibers I know exactly how to identify. And over here, I know that, things over here, and that I compare it to things on that side. I either use row of 1 or row of -1 in order to do my identifications. Okay? So flat structures on V turn out to be exactly, if I want to go ahead and live in this world, these are exactly representations from pi1 of the base into the general linear group, or the orthogonal group if you're going to make your flat structures, okay, or the unitary group if you're working in the complex case and so on. Okay.
What would be not flat in this case?
Okay. So this is, of course, this is really a problem in visualization. Okay, and it's very hard to distinguish. Okay, so firstly, if I did this where row of 1 was multiplication by -1, right, then I produced a Mobius strip in this way. That's clearly, on the one hand, that's a flat bundle, okay, but it's definitely a non-trivial bundle. Okay, so let me just comment, okay. That's the part that part might not be, you might, so, okay. So let's see. So over the circle, there are many, many flat bundles. Okay, because I have the whole general linear group. And this flat structure, right, really means that thing there is rigidly part of the structure. As I go around, I have a monodromy. Okay, so I have this base. Okay, And I don't want to introduce all the terminology of connections, etc. But the basic point is that when I have a flat bundle, you see my fibers should be vertical. Yeah, Da Vinci would not be proud at this moment. Okay, right? I mean, I know how to identify locally all the fibers with each other. And when I'm flat, it means that if I take a little loop, it doesn't go far around, then when I come back to the identity. Okay? I mean, so that's, right? I mean, that's sort of, if you like, the defining feature of flatness. What that means is that if I'm going from one point to another, and I take two different paths, well, if they're nearby paths, okay, there's no problem, and I would still, get the same basis here, giving me the same exactly identical basis there. However, and therefore, if I have homotopic paths, I will still get the same thing. However, if I have non-homotopic paths, then maybe not. Okay? So what you end up getting is a map from, that's what I wrote here, that you get a map automatically from the flat structure. I said that it's equivalent to this, and I don't want to talk about the equivalent. I'm just interested in this fact. Okay, that this flat structure actually gives you a representation. If I had a representation, then I would do the same thing I did there. I would take the universal cover of B, I would cross with the vector space V, okay, and then the group pi1 of B acts on this by covering space theory, and it acts on this via rho. Okay, so then I could go from this down to B and produce a non-trivial bundle this way, okay, just by modding out by pi1 of B. Okay, that's a construction. So this gives you a geometric way. This is a geometric object you could associate to a representation. Okay? That to a representation you get a bundle. Okay? And if your bundle was flat, then you get a representation back. To know that so for every bundle there's this notion of connection, which means that there are ways of identifying this fiber with that one. That's part of the structure, that there has to be such a thing. Okay? But nothing says that when I go here and then I go there and then I go there and I come back, that it has to be the same thing. If I only take small trips, that I don't get any twisting. Okay? So on a Riemannian manifold, okay, so the next comment is, so how do you geometrically think of non-trivial bundles? It's not so easy to think of the Mobius strip is the one that we can draw pictures of. Other than that, it's hard to draw non-trivial bundles. I mean, the tangent space of the two-sphere is something that we can sort of draw. Okay, except that unfortunately the total space is four-dimensional. It's not such an easy thing to fully draw, right? And the fibers look horizontal instead of vertical. It's extremely confusing. Okay, but one of the things that people know is that on Riemannian manifolds there is a canonical identification. Okay, but this is called the Levi-Civita connection. Okay, and it was understood by Gauss already that that when you do spherical geometry, when you sort of transport in the Riemannianly nicest way, along a geodesic triangle, when you come back to the identity, what's reflected here is the area of this triangle. So even very small ones, that's going to give you something close to the identity, but it won't quite give you the identity. Okay? And that's what curvature measures. Curvature. Okay? Okay? So the curvature, okay, measures the non-flatness of the way the bundle was described to you. Right? I mean, you imagine that you're given the E and you're given the projection down, but then you still need to have the identification of the fibers from one nearby point to another nearby point. So that additional structure is called a connection. It could be that if you don't, it might be that the bundle really is a trivial bundle, but you just happen not to have discovered the global coordinates and you did whatever you did stupidly. Okay, so then there'll be something or other that measures that, will measure the fact that even small little loops are going to be trivial. That small little loops are going to come back non-trivially, in the way you did it. Okay? But, one knows that the tangent bundle of the two-sphere is genuinely non-trivial. There is no way to make it flat. Okay? And, right, that's the Harry-Ball theorem, right? That, whenever you go ahead and write down a section, if you write down a tangent vector at every point of the two-sphere, someplace or other it's going to be 0. So this can't be the trivial bundle because, just, the local coordinate v1 comma something would. Okay, so that's a good example. Okay, this bundle, by the time we go to the big general linear group, does become trivial. Okay, and that's the fact that if I take the tangent bundle of the sphere and I add a line bundle, the trivial line bundle, namely the unit normal vector, then I can produce 3 vectors at every point, namely the x, y, and z vectors at every point. That would be a frame everywhere. So there's sort of a lot of, so by going to the infinite one does throw away phenomena. Okay, and subtle phenomena and interesting things. Okay, all right. So far we have. Okay, now I have to tell you.
That's always true. So there aren't situations where you go to the infinite and there's still something non-trivial?
Oh yeah, no, there is, and that was that z, z2, z2, 0, z, 0, 0, 0, z. That's all that's left. Okay, so for example, so over the so for over the 4 sphere, there are infinitely many real bundles that stay non-trivial no matter how high the dimension you go. Okay.
Over the 2 sphere, there's 1, and there is also infinitely.
Over the 2 sphere, there were infinitely many complex bundles. Okay, and over the 4 sphere, there are infinitely many real bundles. Okay, and this is going to reflect me constructing over hyperbolic surfaces. I will construct almost flat. I'm going to steal from Gromov and Lawson the construction of almost flat unitary bundles, and over hyperbolic 4 manifolds, I'll describe for you almost flat real bundles, orthogonal bundles. Okay, but it's going to be the exact same construction. It's just that you have a little less input. Okay, so I don't want to, so curvature. You don't really need to know the definition of it. You need to feel it. Okay, I mean, the definition is just a matter of obscuring what you feel. Okay, and making it precise. Okay, I mean, it's like defining love or something. Okay, so that's my warning that I have 10 minutes left. Oh, so. Okay. So, but you know what it is? It has to do with, when you're going on sort of loops of a certain size, how much have you deviated from being the identity, right? I mean, how much are your bundles twisting over limited scale curves? Okay, right? I mean, okay, so, and now a comment is that sort of the twisting of bundles over B can be measured by what are called characteristic classes. Defined using curvature forms. Okay, and they live in either H2I of B with coefficients. I'll just use, this is where Chern originally put them, so I'll put them there. Okay, and in the real case, so this is for the complex case, and over the reals, it's an H4I. Well, then Okay. So these are called Chern classes, and these are called Pontryagin classes. It doesn't really matter what, their definitions, but these are ways of measuring the non-triviality of a bundle, and they detect actually all the infinite information. Okay, that's, I don't know if that's a theorem of Hopf or Grassmann. I mean, I have no idea. I can't even guess which century it's true. Probably, but it was known to. Yeah, it probably wasn't Grassmann. But I could make cases. I could give it to many dead mathematicians. Okay, that these are how you understand things. So now here is the question. Okay? Suppose that I have a vector bundle, E over B, and it has a bunch of connections. Yeah, no, so the connection is the way that you move from one fiber to the other. Okay? I mean, it has some formalism. Along a curve, right? You go, okay? Right, so you're given a curve. Here you have B, here you have another point, and you have some curve that connects them, and you want to get an identification from this to that. And, so you have to write down in math what that means, what kind of linear maps, blah, blah, blah. What kind of differentiabilities, and then a connection provides you with this data. Or it's some, it's as convoluted as a tangent vector being a derivation on the germs of C infinity functions. It's a proper definition, but it obfuscates the matter. I don't want to, do the same now. Okay? Okay, so suppose that you have that the curvatures of these connections are going to 0. Okay? Right? So this might be a notion of almost flat. Okay? So then,
What is going to infinity there?
it has a bunch of connections. So I have
Sequence of connections.
a sequence of connections, right? So I think of the vector bundle as being a basic object, but then I keep changing my mind on how I'm going to identify the fibers with each other. Okay? So now this turns out to be, this implies, at least if B is compact, that it is flat. Okay? I mean, that it really has a flat structure. This isn't where it comes from, with a fixed fiber dimension. Okay? Okay? However, suppose that you now have a sequence E sub I, and these have a bunch of connections, lambda sub I, and these curvatures go to 0. Does this
Now only with I going to infinity.
right. Yeah, and the fiber dimensions are going to be going to infinity.
Is this like the dimension of V earlier?
Yes, this is the dimension. This is dimension of the fibers, right? Okay, you're going to allow your dimensions of the fibers to go up. Okay, and what I want to explain is that this does not imply that E has a flat structure. That any of the EIs have a flat structure. Okay. Okay, so let me explain the construction. I mean, I don't want to go so far as to make this precise enough. Remember, I said there are going to be no theorems, right? I mean, and if I'm not careful, this could turn into a theorem. Okay. Okay. So here's the idea of Gromov and Lawson. Okay. So the first thing is, we'll start off with the surface of genus 2.
What's the connection between EI and EI plus 1?
None. 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 Just like in the previous talk.
So why would I expect EI?
Oh, well, if you had EI and they all had the same fiber dimension, then ultimately for I sufficiently
If I had EI,
Ah.
EI plus 1 has nothing to do with
right,
EI.
but yeah. So here's the point.
Suppose EI plus 1 had a flat connection. Does that imply that EI?
No. So here's the point. Okay, yeah. All right. Yeah, no. So you don't understand the connection between the There really is none, just like there was no connection in the last talk between the various almost representations in the almost representation, so to speak, right? I mean, the various things that were approximately, that were approximate homomorphisms, right? I mean, they were just a sequence with different groups. Here the point is that if I have a constant fiber dimension, then there's a threshold epsilon, such that if the curvature is less than epsilon, I can actually make the curvature 0. Okay? And what I want to say is that by allowing the fiber dimension to go up, that the threshold epsilon in the operator norm is going to 0. Okay? Okay? All right. I didn't write that but okay? And okay, and that clarifies what the content of the theorem is and gives it an intellectual context. Okay? I fear that I'm not going to get to explain why Gromov and Lawson were interested in this, which is, I think even more interesting than the fact that these exist. But so here's how it goes. So the first thing is we'll go to a very big cover. a large girth cover. Okay? The only thing that that uses about this fundamental group is that it's residually finite. Okay, so I mean, don't think that I'm doing expanders or anything. So by large girth, right, I mean, all that I mean to the Riemannian geometers, I mean that the injectivity radius is large. So that means, okay, I don't really even need it to be a regular cover. I just need there to be a big ball inside. Okay, so this is a big B2. Now remember I told you that there are infinitely many vector bundles over the two-sphere that are really stably non-trivial. So let me just use one of them for once. Okay, and now I'll just pull this back. Well, I can't pull it back until I have a map, right? So the map is I'm going to take this ball and I'm going to wrap it around the two-sphere. Okay, and all of this stuff here I'll send to the point 0, right? This two-sphere is the one-point compactified Riemann sphere. Okay, so, okay, voila. Okay, I have this. Okay, and now this will have some connection that it comes from here, right? I mean, out here the bundle is really trivial, right? It's a constant map, so all the fibers are the same. Okay, what's going on here, it has to do with what's going on here. If I have a curve here and I want to know how the fibers compare, I'm comparing it with what's going on here. Okay, so what will the curvature be? I don't know, it'll be whatever it is. Give me a break. Okay, now, suppose that I do this with a parameter r. I go to an even bigger cover, okay? And now I ask what's going to, right? I go to this bigger cover, and now I do this. Well, you see, this map here is, right, I mean, the length of curves is getting multiplied by something like 1 over r. Right, as I go from here, right, the ball of radius r, I'm mapping it, to the two-sphere, right? I mean, I could, if r is bigger, I mean, I'm shrinking, right? So if I have a curve in a small neighborhood here, it's, it's having less and less curvature, as I vary this construction. Okay. However, I achieved nothing. One could argue, okay, because I had a sequence of bases. For each base, I had to, right? I had to, So let me point out. The fiber dimension hasn't yet gone up.
Right, because you take the bundle to be fixed.
Here, the bundle here is fixed, right? So when I do this, I'm changing the base each time. Okay, so what I have is less and less curvature over different bases. Now, of course, these bases, they're comparable to each other. They're all hyperbolic manifolds. I mean, it feels like there's something going on. But now there's another construction. Okay, so if here I have B1, and here I have B, and here I have a covering map, okay, and here I have E. What I claim is that there's a thing called pi push forward of E that lives over B, and pi push forward of E is just the sum of the pi inverse of the E. I can't do notation. So let me draw the picture. If here's a point B, it has a bunch of inverse images, right? Because the number of sheets of the cover, right? It's always the same number. And then over each of these points, I have the vector space associated to that. And now what I could just do is take the sum of all of those, and that will be a varying family of vector spaces. Okay? And now, if you look at what's going on in a coordinate chart, what's going on is exactly each of these separately. Okay? So now what's happening with a curve? Oh, well, if I went to a very, very high sheeted cover, then the Lipschitz constant of this map is very small. Right, so the curve's gotten a lot shorter here. So obviously the curvature, you feel that it's going to 0. Okay, so now the only thing that you need to know is, did I produce a trivial bundle or not? So this is a construction of bundles. It's a construction of almost flat bundles. Right, I mean, it's clear that they're getting, yes? Yeah, right, so that I could do this construction. On the torus, I could do it too. I have to unwrap 2 directions, right? I would take exotic rectangles because instead of doing squares, just because I'd like it to be prettier. I think it would be a nicer picture. Okay? but that's an aesthetic judgment. Yeah, you go to Z mod n cross Z mod n, and that would be good enough, right? You don't need expansion, as I said. You just need residual finiteness. Okay? I mean, okay, so anyway, so this is the construction. This produces almost flat bundles. And now, if I explain to you, basically what happens is there's a two-dimensional cohomology class here, which is non-trivial. That's what reflected this bundle being non-trivial. This map has non-zero degree, so it has non-trivial cohomology here. And this map here is multiplication by the number of sheets in the cover. So what happens is that the Chern class of this bundle, of this construction, is in fact going to infinity. Okay, so they're definitely not becoming trivial bundles. You're detecting them topologically. Now, Gromov and Lawson had some very good reasons for wanting these kind of bundles. And now let me just make the additional comments. You could do this in the real case just as well. I could have done G mod K mod gamma for any semi-simple group as long, yes?
So now you're saying that this is an almost homomorphism.
Yeah.
Because
Yeah, so the almost homomorphism is you choose generators for the fundamental group and you choose actual curves. Okay? And then when you go around a curve, if you take an element in the fundamental group, you write it as a word. Okay? You follow those specific curves around, and then and you go ahead and you see, okay, that as you go around a curve that represents the trivial element in the group, when you come back, you're near to the identity in the operator norm. That's the sense in which it's almost flat.
in all of them.
Yeah. I mean, as R goes to infinity, you're getting closer and closer to the identity in the operator norm.
Do you understand it correctly that in some sense the almost homomorphism that you get here, it itself is a limit of almost homomorphism of the finite quotient if you would take here the regular sheeted cover?
No, I don't think so. I'd have to think about it a little more carefully. I have to, there's this key thing here where you're using what's called the Bott element. Right? I mean, you use a specific, right, and that's getting pulled back here. I mean, that's sort of the basic unit, and then that's getting. So I don't think so.
The almost property follows from the curvature.
Right. But so anyway, so what's happening is you're discovering that there are bundles that are topologically non-trivial, and that they're closer and closer to having a representation theoretic description, so to speak, right? I mean, the curvatures are going to zero, so you could go ahead and do it on particular representatives. You can't go ahead and say, oh, on this homotopy class of curves, I know what the monodromy would be. No, you have to pick a specific curve to talk about the monodromy, but the relations almost hold.
And some of you read that they are not flat because of this. What happened with this?
Because of the characteristic classes, because of the Chern class, right? And
What because the classes should vanish?
they vanish because what happens is the characteristic classes are measured locally in terms of the curvature. The formula that Chern gave for Chern classes is, the curvature gets incorporated into a two form, and then you take powers of that two form. It would have to be, if it's flat, the form is identically zero. Okay, so, so here what happens is that form is small, but the integral of something is, over the whole volume, is non-zero. And that's what you're detecting. That integral is a well-defined feature of the bundle. That was what Chern showed, that these characteristic classes of bundles don't depend on which connection you put on the bundle. It's like knowing that the tangent bundle of the two-sphere is non-trivial because the Euler characteristic is non-zero. Right? I mean, that's something or other that you do, you can measure off any vector field. Okay? So anyway, so that's sort of the idea. And then for buildings, you do the same thing. You again would pass to a big cover. You'd find a big flat inside. Now, unfortunately, the picture isn't quite this simple. You have to fold the rest into that big flat. Okay? And then you have to do some other integration in order to check that you don't get a trivial bundle. Right? So you have to know that there's some cycle that goes through that part of the building. But if you want to have some S-arithmetic situations where you get such non-trivial bundles, you could produce them by a variation of the same method. But by the way, my time is more than over, so I think. So firstly, I feel entitled to some clapping. And then, okay, thank you. All right, and now I can answer whatever question. One thing, you're supposed to. Okay.
What's the statement for the building?
No, so if you were to take one of these usual buildings so that the cohomology is there in the top, and then you make, and that top dimension is even or a multiple of 4. In either of those situations, then, you could go ahead and produce a sequence of bundles in this way. So then there will be an almost homomorphism that's not an almost homomorphism.
Why do you need anything about B, that B would be even dimensional?
Yes, remember, where did you use that? Because remember, B was this hyperbolic manifold, right? So this is hyperbolic space. This ball here, I'm going to the 2-sphere because this is 2-dimensional hyperbolic space. Okay? I mean, there might be additional tricks you could do in other dimensions, right? I mean, the obvious thing to do is I have something of dimension 3, I cross with a circle, and then I take Z mod n cross those covers, and I get an almost homomorphism of Z cross gamma. And then you could ask whether that almost homomorphism, when restricted to gamma, is non-trivial, and I don't want to think about it. I mean, I'm sure it probably is, but, yeah.
So, from a classifying space point of view, this gives you a little more than what the group theorists here often do, because you're actually getting maps from the base into classifying spaces of unitary groups of a bunch of maps, right? So maps from B to a product of BU, BIs, right?
Yeah.
Right? And then you're saying that the curvatures are going to 0 in the limit.
Right.
Right, and so you can't produce, and if you give the unitary group a discrete topology, you can't lift it to, there's no flat bundle inducing that map in the limit, right? So that's what you're saying. So you get a little
Right.
more.
Yeah, so probably I could use some non-standard language to say what space what's being mapped into.
You formulate your theorem in terms of classified spaces.
Yeah, probably a non-standard BGLV enters. That you have a map, that ordinary bundles are mapped into BGLV, that sort of almost flat bundles are into some kind of non-standard BGLV with the discrete topology, and you're asking the difference between that and B of GLV with the genuine discrete topology. That's probably linguistic, I mean, whether it helps, I'm sure, I don't know, if I could give a beautiful talk as Glebsky, then yeah, it'll help a lot. But I don't know. I mean, let me just comment that the later papers of Grobov and Lawson, and with Kahn and Moscovich, take this idea, but they go and they deal with infinite dimensional, almost flat bundles. Their interest was what happens if you want to show that, say, a non-positively curved manifold doesn't have a metric of positive scalar curvature, and the problem is that you don't know that the fundamental group has any subgroups of finite index. Right? I mean, it's just this kind of crazy group gamma, right, that you don't know anything about. And so, but they said one group they know about, which is the universal cover. But in the universal cover, then, if you were to do this, you'll have infinitely many sheets, right? So it's an infinite dimensional bundle. So there's a question about in what ways can you make use of infinite dimensional almost flat bundles. So that's the direction that their later work goes. And they show that those are extremely valuable for problems in differential geometry and in topology. Okay? I feel bad. I mean, I wanted to explain all of that stuff, but I don't know. After lunch, anyone come back? No. Okay. I think that's it.